Hey everybody, welcome back to the channel. Today we're talking about free body diagrams. Free body diagram is a diagram that we use to show the magnitude and direction of all the forces going on in a situation. So the previous video is probably one that you want to make sure you have looked at all the terms from. There's a lot of vocabulary that happens in the previous video. There will probably be an not Edpuzzle, but a Quizlet deck for all those terms coming at you real soon. Use that if you need to have help learning those terms, because you're going to be expected to use them throughout your writing and various lab reports and various problems that we're going to be encountering. You're going to be expected to be fluent in those words. And free body diagrams is another place where fluency in those terms is going to be really important to your success and getting A's and B's in the class. So ultimately, when we're drawing a free body diagram, we represent whatever we're looking at as a box. This doesn't matter what it is we're looking at. It could be a car, it could be a person, it could be a kitty. All the things are going to be a box. Okay? And what you're going to do is you're going to draw a force. You're going to draw it as an arrow. The direction is going to show the direction that the force is acting. Okay? Each arrow is going to be labeled to say what type of force it was. So if you go back to the previous video, you'd see that there was applied force, normal force, friction force, gravity, all these things, and that they're all kind of labeled out for you. Okay? The only rule is that you got to depict all the forces that exist for that object in the given situation. Ultimately, you want to draw a box, label all the arrows in the appropriate direction, and use size of arrows to try to show relative magnitudes. That's not terribly important, but it is something that you're going to want to do as you get refined. If two forces have the same value like the normal and gravity often do, you're going to want to draw the normal force and the gravity force with the same size arrow. If you're dealing with something that is a greater applied force than the friction force in this one's kind of a bad example because the friction and the applied are the same. So if I were drawing this, I might expect that the object isn't necessarily moving in this case, because it looks like friction and applied force are the same, so the applied force hasn't really overcome static friction. Like this example here might be someone trying to push a refrigerator, and they're not getting it to move yet because of the way it's drawn. Okay. At first, I'm really just happy if you can label all the arrows right. But eventually watch your magnitudes. Watch your lengths of your arrows, because that does have meaning. So the way these problems work is that a physical situation is going to be described. We're going to draw a box and then make a bunch of arrows that show what's going on. Okay. So our first one here is we got a book. It's at rest on top of a table. Book at rest on top of a table. So the way that looks is I would draw a box. My box is my book in this case. The force of gravity is pulling the book down onto the table. The table is opposing the gravity with the normal force. And those two would be equal in opposite directions. One's going down, one's going up. There's nothing else happening to this book. So this would be the free body diagram for a book sitting at rest on a table. In this problem, we got an egg. That egg is free falling from a nest, and I'm told to neglect air resistance. Oftentimes, we do neglect air resistance because air resistance is really hard to calculate. You can actually get really far in college and not have to deal with air resistance because it's a real pain. Okay? So oftentimes you're going to be told to just neglect air resistance. That means that ultimately I got a box representing an egg and it is just fallen. If I were to draw air resistance, it would be a vector coming up the top. It would say F air, and that would be it. But because I'm told to neglect air resistance in the problem, I don't draw it. There's nothing making it go left or right, so all we got is gravity yanking it down. In problem 3, we got a flying squirrel. That flying squirrel was gliding without wing flaps from a tree to the ground at constant velocity. Constant velocity. Think back a couple days ago. Constant velocity has an important meaning. Constant velocity means my acceleration is 0. That means there's 0 force. Consider air resistance. A free body diagram for the situation looks like this. We got to make a box for the squirrel. The squirrel is being pulled to the ground by gravity. Air resistance is pulling the squirrel up, opposing that gravity. And we know there's no other forces forward or back because the squirrel is moving at constant velocity. There's no applied force. The squirrel isn't flapping its wings to go faster. It is simply gliding to the ground. Here I got a rightward force that's being applied to a book in order to move it across a desk. Consider frictional forces. Neglect air resistance. Construct a free body diagram. All right, so what does this one look like? We're going to have a box. It's going to represent our book. We're going to have a rightward force moving it across the desk. Friction opposes that motion, so friction's going to the left. We're going to ignore the air resistance. Is there anything else, though? What else is going on with the book? Gravity. Gravity. So gravity is pulling the book down. Normal force is pulling it up, pushing it up. Notice that the frictional force is drawn smaller than the applied force. That means that I am in motion. Friction is not overcoming the applied force. That's shown by the difference in their size. Notice that normal force and gravity are of equal size, and those cancel each other out. This one kind of illustrates the big rule of free body diagrams, which is you need to show all the forces going on. So you want to show the gravity and the normal force, even if they're not necessarily relevant to your calculations. The other big piece that I like about problem 4 here is that we see the size difference between friction and the applied force. That's really important for us because that tells us that this is in motion. Okay? If you aren't drawing your vectors to some sort of scale, then you can be very misleading to a person trying to analyze your picture, and you could also mess up yourself. One more problem here. A car runs out of gas as it's coasting down a hill. No gas means I can't use the gas, right? So I can't accelerate with gas. What's going on here? Well, I've got gravity, right? I'm not falling through the asphalt, so there's got to be some sort of normal force counteracting that gravity. And there is friction from the road. The road's going to oppose the motion of the car, but there's no ability for the car to accelerate because it's out of gas. That is, in essence, what free body diagrams are about, folks. You look at a physical situation and you draw a box for whatever the object is, and then you draw a bunch of vectors. I hope that makes sense to you, and you're going to be getting a lot of practice with this over the coming months. So if you didn't quite grab all this. I was just watching the previous video where we talked about types of force, and then watching this one again, and hopefully getting a better grasp of these things. Come see me if you need help, and expect to see practice on these in both labs and handouts in the future. Have a great night, everyone, and I'll see you in class tomorrow.